The history of aerospace engineering is fundamentally a history of energy conversion, the struggle to translate the chemical potential energy of fuel into the kinetic energy of a vehicle with maximum efficiency. In the early 20th century, rocketry was synonymous with black powder, a low-energy solid propellant that offered poor specific impulse and uncontrollable combustion characteristics. The transition from these pyrotechnic curiosities to the high-energy thermodynamic machines that define the modern aerospace era is largely attributable to the theoretical and experimental rigor of Dr. Robert Goddard. Goddard's work, particularly between 1915 and 1941, represents a systematic dismantling of the thermal and fluid dynamic barriers that prevented sustained supersonic exhaust velocities. While his public legacy often focuses on the spectacle of the March 16, 1926 launch, his technical relevance to modern aero-engines lies in his mastery of two critical domains: combustion efficiency via the adaptation of the Laval nozzle, and thermal behavior through the development of regenerative and film cooling techniques. The engineering challenges Goddard faced were not merely structural, but deeply rooted in thermodynamics and fluid mechanics. He had to conceive of a heat engine that operated at temperatures far exceeding the melting point of its constituent materials, and he had to motto a method to convert that thermal energy into directed momentum with an efficiency that surpassed the steam engines and internal combustion engines of his day. This report provides an exhaustive analysis of Goddard's engineering methodology, examining how he applied the laws of thermodynamics to rocket propulsion to solve the complex problems of propellant atomization, combustion instability, and heat flux management that remain central to jet and rocket engine design today. In 1915, the state-of-the-art in rocketry was the Coston signal rocket, a device used for maritime signaling. Goddard's initial ballistic pendulum experiments at Clark University revealed a dismal reality. These powder rockets converted only about 2% of their thermal energy into kinetic motion. The remaining 98% was lost as waste heat, inefficient expansion, and unburned propellant. In contrast, the piston engines of the era achieved efficiencies of around 40%, and steam engines approximately 21%. For rocketry to become a viable method of high-altitude sounding or interplanetary travel, Goddard realized he needed to close this efficiency gap. He hypothesized that the rocket could become the most efficient of all heat engines if the exhaust gases could be expanded properly. This realization marked the pivot from ballistics, the study of projectiles, to propulsion engineering, the study of thermodynamic cycles. Goddard's 1919 publication, A Method of Reaching Extreme Altitudes, laid the mathematical foundation for this shift. He calculated the energy density required to escape Earth's gravity, identifying that solid fuel was insufficient due to its low exhaust velocity. His calculations pointed toward liquid hydrogen and liquid oxygen as the ideal propellant combination, offering the highest theoretical specific impulse. However, the engineering community and the public struggled to grasp the physics of reaction engines. The infamous 1920 New York Times editorial, which mocked Goddard for lacking the knowledge ladled out daily in high schools, stemmed from a fundamental misunderstanding of Newton's third law. The critics assumed a rocket pushed against the atmosphere. Goddard's vacuum chamber tests in 1915 proved definitively that thrust actually increased in a vacuum by approximately 20% compared to sea level, as the absence of back pressure allowed for greater expansion of the exhaust gases. This was the first experimental validation of the nozzle theory that would dominate his later work. The primary metric of a rocket engine's efficiency is its exhaust velocity. The relationship between thermal energy and exhaust velocity is governed by the conservation of energy, where the enthalpy drop of the combustion gas is converted into kinetic energy. To maximize this conversion, Goddard looked outside the field of rocketry to the domain of steam turbines, specifically the work of Gustave de Laval. The de Laval nozzle is a convergent-divergent device designed to accelerate a gas to supersonic speeds. It operates on the counterintuitive principles of compressible fluid dynamics. In a subsonic flow regime, Mach less than 1, a gas accelerates as it passes through a converging duct, decreasing area. However, at the throat, where the cross-sectional area is minimal, the flow reaches sonic velocity, Mach 1. This is the choked flow condition. To accelerate the gas further into the supersonic regime, Mach greater than 1, the duct must diverge, increase in area. This is because, at supersonic speeds, the density of the gas drops faster than the velocity increases, requiring an expanding volume to accommodate the accelerating flow mass. Goddard was the first to apply the steam turbine technology to a rocket engine. By threading various nozzle designs onto a solid propellant combustion chamber, he observed a dramatic transformation in performance. Velocity increase. Jet velocities jumped from the standard approximately 1,000 feet per second of powder rockets to between 7,000 and 8,000 feet per second. Efficiency jump. The thermodynamic efficiency of the system leaped from 2% to approximately 63%. This application of the de Laval nozzle essentially birthed the modern rocket engine. It transformed the rocket from a pressure vessel that vented gas into a sophisticated thermodynamic machine that managed enthalpy conversion into kinetic energy. Goddard's early experiments primarily utilized conical nozzles. While easier to manufacture than the complex curves of a bell nozzle, conical nozzles suffer from divergence losses. In a conical nozzle, the exhaust gases near the nozzle wall have a velocity component perpendicular to the thrust axis. This radial momentum does not contribute to forward thrust, representing a loss in efficiency. The bell nozzle, or contoured nozzle, which Goddard later approximated in his L-series and P-series rockets, minimizes this loss by turning the flow near the exit so that it is parallel to the rocket's axis. However, the manufacturing complexity of creating a regeneratively cooled bell nozzle in the 1920s and 30s forced Goddard to rely heavily on conical geometries with varying expansion ratios. The visual signature of Goddard's high-efficiency combustion was the presence of shock diamonds, also known as Mach discs, in the exhaust plume. These standing wave patterns are the visible manifestation of supersonic flow adjusting to ambient pressure. When the exhaust is overexpanded, as is common at liftoff for a nozzle designed for altitude, the ambient atmosphere compresses the plume inward. This creates oblique shock waves that reflect off the center line of the flow. Mechanism. The compression raises the temperature of the gas adiabatically. In Goddard's gasoline and liquid oxygen engines, the exhaust was typically fuel-rich to keep temperatures manageable. When the gas passed through the shock wave, the sudden spike in temperature and pressure caused the unburned gasoline to ignite, creating visible bright diamonds or discs in the flame. Sensory evidence. Goddard described the launch not as an explosion, but as having a steady roar and a lack of smoke. This auditory and visual shift, from the bang of powder to the roar of fluid dynamics, signaled the transition to supersonic, continuous combustion. The shock diamonds were the optical proof that the de Laval nozzle was functioning correctly. Goddard's second major leap in combustion efficiency was the transition from solid to liquid propellants. While the Russian theorist Konstantin Tsiolkovsky had proposed liquid hydrogen and oxygen in 1903, Goddard was the first to tackle the immense engineering challenge of handling them. In his early theoretical work, 1909 to 1914, Goddard correctly identified liquid hydrogen and liquid oxygen as the ultimate high-energy propellant pair. Hydrogen offers the lowest molecular weight. However, in the 1920s, liquid hydrogen was a laboratory curiosity, difficult to produce and store. Goddard made the pragmatic engineering decision to use gasoline as the fuel and liquid oxygen as the oxidizer. The thermodynamic potential of liquid oxygen and gasoline is useless if the engine melts before the vehicle leaves the ground. Goddard's work in thermal management is arguably his most significant contribution to the longevity of propulsion hardware. He moved through 3 distinct phases of cooling technology, each more sophisticated than the last. Initially, Goddard attempted to insulate the metal walls using refractory materials. He lined his steel combustion chambers with alundum, fused aluminum oxide, and placed layers of asbestos between the liner and the steel shell. In 1931, Goddard introduced a copper water jacket that fit snugly around the combustion chamber and nozzle. Goddard is credited with the first practical implementation of regenerative cooling, a concept he had considered as early as 1923, but initially rejected as too complex. By the late 1930s, he had refined the technique. Alongside regenerative cooling, Goddard pioneered film cooling, which he referred to as curtain cooling. This technique is extensively used in modern gas turbine engines, jet engines. High-performance turbine blades are perforated with tiny holes that allow compressor air to form a protective film, enabling the turbine to operate in gas streams that exceed the melting point of the blade's superalloys. While the nozzle and cooling systems address the combustion and thermal angles, the delivery of high-energy fuel required a mechanical revolution that bridges rocketry and aviation. Early Goddard rockets, like Nell in 1926, were pressure-fed. A tank of high-pressure inert gas, nitrogen, forces the fuel and oxygen into the engine. The penalty was, to hold high pressure, often 200 plus pounds per square inch, the propellant tanks had to be made of thick, heavy steel. This weight penalty made high-altitude flight impossible. So, to solve the weight problem, Goddard realized he needed low-pressure tanks, lightweight, and a high-pressure engine. The solution was the turbopump. Goddard's development was not a straight line, but an iterative process of failure and refinement. Analyzing his specific series reveals the evolution of his thermal and combustion strategies. Dr. Robert Goddard's contribution to engineering is defined by his refusal to accept the thermal and efficiency limits of his time. He did not merely invent a machine, he designed a thermodynamic system. Goddard's work was the bridge between the intuition of 19th century inventors and the rigorous thermofluid dynamics of the space age. Every modern aero-engine that utilizes a convergent-divergent nozzle or cools its walls with its own fuel is operating on principles demonstrated, often for the first time, in Goddard's lonely test stands in New Mexico. He proved that the barrier to space was not gravity, but thermodynamics, and he solved it.